All right, welcome back to Physics 325 online edition. Today we're on lecture 29 out of 30, so we're almost there. And what we're going to look at today are three kind of key optical instruments. The eyepiece, also known as the magnifying glass, the compound microscope, and the telescope. In the last class we looked at a very important optical instrument, namely your eye, and it's important to treat it as an instrument because its operation is really crucial to understanding the operation of the other instruments we're going to talk about today. So we have to use the fact that our eye has a lens in it and can cast even a virtual image. It can cast rather a real image of a virtual image onto our retina. So we're going to start off with the simple magnifier. Let's dive into that. So the simple magnifier is effectively a single lens, usually with a tight focus. And the whole point of the magnifier is to make something nearby and small look bigger. But first we have to ask, what does it mean for a thing to look bigger? So suppose we imagine something small. I don't know, I'm a nerd, so let's imagine Arya Stark from Game of Thrones. Say she stands at about, 4'5", and next to her is standing the mountain at about 7 feet. So, in this picture, clearly the mountain looks bigger. The mountain is bigger. However, let's make the mountain, or ask the mountain very politely, to stand 20 meters back. And little Arya, let's say she's about 5 meters back. So now, in fact, she looks bigger. Why? Well, she takes up more field of view. And if we recall our discussion from yesterday, that means that the physical image on your retina as you're looking at this scene of Arya is bigger than that of the mountain. So our goal is to make something look bigger. We want it to take up more angle. And this gives us a clue at how to make the simplest possible magnifier. We can use our hand. Say we grab something small we want to look at, an ant. We can bring it closer and closer to our eyeball. And it will look bigger and bigger because it will take up more and more angle. So we have our ant, and it's some distance away, and it takes up some angle. Now we'll move it closer. We move it closer, and the ant looks like it takes up a lot more of the image on our retina. But there's a problem with that. Of course, we can bring it closer and closer, and it will take up more and more angle, and therefore it will look bigger. But there's a problem with that. We can only bring it so close as to physically touch our eyeball, which would be gross. But besides the fact that it would be gross, we saw last class there's some closest distance called the near point, which is 25 centimeters on average, after which our eyes can't accommodate enough to form an image on our retina. So that actually puts a physical limitation on this. We cannot bring an image closer than that near point. So this is where a simple magnifier comes in. We can place something closer than our near point, and then put another lens, a converging lens, even closer than it, so that it forms a virtual image laying farther away than our near point. Let's draw a picture of that. So here we've placed a lens in front of the object, and the object is within the focal length of the lens. Therefore, it will cast a virtual image. And that virtual image, it actually consists of diverging rays, so we can't form an image on a piece of paper. However, our eyes can converge it, and it looks as though there's a giant ant past our near point that we can therefore resolve. And we get a much larger angle subtended by that giant ant. Let's make this a bit more quantitative. We can calculate the amount of increase in angle, or the increase in apparent size that we're going to get. Now, we have some freedom as to where we want that virtual image to go. We can wiggle the magnifier around a bit. So we can place it at the near point. Let's have a look at that. So let's assume that we're going to place this image of the ant right at the near point, right here, where that dot is, and see what that tells us. Now we can just apply the thin lens equation and multiply both sides by di. And this is the magnification when you place the virtual image at the near point. But as you may have tried last lecture, if you place something very close to the near point, it's very hard in your eyes. Your eyes are constantly straining to bring the image into focus. So a better solution is to place the image at infinity. Place the virtual image at infinity. And effectively what this means is your eyes do not have to strain. They're perfectly relaxed and they still form an image. So let's look at that. First of all, we have to understand, we have to think about what it actually means, and what the magnification means as compared to an object at infinity. Effectively, it means that we're comparing the angular size of the object subtended by the object as compared to the case where it was at the near point. Okay, so that means, that is to say, that the magnification, when the image was originally at the near point, we have magnification is equal to 25 centimeters divided by the focal length of the lens. And that is the magnification of the eyepiece when you image the object at infinity. Slightly less than at the near point, but much easier on the eyes. And there's more fancy eyepieces than a single lens. We'll talk about those next lecture. But that's basically how an eyepiece works. Looking at the formula for magnification by a single lens, we see that there's some limitations. To get a truly large magnification, we need a really small focal length, which means a very tight radius of curvature, and that's difficult to manufacture. There's also other problems with that. You don't want to use too much of the radius of curvature of the lens because our small angle approximation, which we've been using this whole course, will fail. That will lead to defects in the imaging known as spherical aberration, which will be discussed next class. So we're stuck with an intermediate magnification. And how do we improve that? Well, a much better design is to use a two-lens system in what is known as a compound microscope. So the compound microscope consists of two lenses. We have a tight-focused objective lens, and then we have a magnifying glass, a simple magnifier, or an eyepiece, that we studied a moment ago. So let's move this over so we can sketch it out. Now the basic functionality of the compound microscope is as follows. We take our bug, or whatever it is that we're trying to look at, and place it on a stage. Our strong focusing objective is placed close to the bug, and it's going to be not so close that it's within its focal length, so it's going to create a real image. There's our bug, and it's going to create a real image of that bug. So step one is to create our real image with the objective. And that's going to have some magnification. We'll call it M1. It's negative because it's a real image, so it's going to be inverted, and it should be rather big. Now that's similar to our simple magnifier. We're now going to use a simple magnifier to make an image of the image. All right. So now notice that this bug is within the focal length of the eyepiece. So we're going to make a virtual image of our image and get a large magnification. And that's how it works. We have our terrified observer here as usual, and they see this inverted image of the bug. Inverted because the first magnification was due to a real image, and the second one was a virtual image, so it didn't re-invert it. And that's what you see out of your compound microscope. So we'll call that step 2. And that's how the compound microscope works. Now let's take a look at one of these things. So here's an example of a compound microscope. I happen to have one in my closet. And we can see some of the details that we're talking about today. So this is the compound microscope, an example of it. Here we have the eyepiece up here and the objective down here. And as mentioned, we have a little jig here where we can rotate between objectives to get different magnifications. And the eyepiece can move in or out in order to maintain focus. And here we're using what looks like a 20 times magnification. So that would be a focal length of about 1.25 centimeters. So to see how it operates, let's take a sample of something. We have some seaweed here, just 'cause. And we'll look at it under the microscope. So we'll load the sample in. Flick on the light from underneath, and we'll replace the eyepiece trusty CCD that we used for the pinhole camera that came with the microscope. And let's just see what it looks like on the computer. Okay, so we'll find focus. This is on the 4x setting of the objective. There we go. That looks pretty neat. This is dried seaweed, by the way, collected by my assistants. Let's try 10x magnification. I'm just flipping the objectives here, and you get a bit more resolution. Quite neat. We can move back and forth along the sample. See various features. Very neat. And let's try going to 40x. Have to refocus slightly. Oh, very cool. That's what it looks like there. There's also an oil immersion lens on here, but we won't go there. And that is how a compound microscope works in practice. So let's try to sketch out what's going on and try to find something quantitative about what's going on with this microscope. The length of the distance between the two foci here is a standard. Just like there's a standard predefined near point, there's a standard tube length, which is 16 centimeters. Now this is technically the distance between the two foci, but usually the foci, are very small compared to this L. And the total magnification is just the product of the magnification of the intermediate image times the magnification from our simple multiplier. So let's try to sketch this out. The magnification of the intermediate image is given by the image height over the object height, with that minus sign there. And that's given by the image distance to the object distance, as we found last time. Now the image distance is going to effectively be the distance to the eyepiece, because we're going to put it very near the eyepiece's focus, We're going to put it very near the center. So this is going to be L divided by the focus of the eyepiece, because you're going to put your image right near the focus as well to make a big image. So this is to say that this distance here is approximately equal to the focus of the eyepiece. Now, the focus of the objective is much smaller than L typically. And we're going to place the image, or the object rather, very near this focus. So we can approximate this as the image distance to being very close to L here, and the object distance about equal to the eyepiece. And that gives us the magnification, technically the first magnification of our intermediate image, is 16 centimeters, the tube length, divided by the eyepiece focus. And then we just look at the image that we form with a magnifying glass. We've already worked out the magnification in this case. It's usually best to put the object that we're actually seeing at infinity, meaning that the rays are going to be pretty much parallel coming into your eye. In that case, as we found out last section, the magnification is 25 centimeters over the focal length of the eyepiece. So the total magnification of the compound microscope is the product of M1 times M2, which is 16 times 25, or 400 square centimeters, over the product of the focal lengths. Now, if you're just plugging in numbers, you better put those focal lengths in centimeters, or else you'll be getting something very odd. But this is way better. So if we have our typical 10x eyepiece, the focal length is 2.5 centimeters, and the objective can be very short as well. Maybe it's 4 centimeters, even though it's probably going to be smaller. I just did that because the numbers will be easier. That gives us a magnification of 40 times. We can typically make objectives with much shorter foci, a tenth of that. So we can easily get 100 or a few hundred even magnifications with the compound microscope. Okay, so the final instrument we're going to discuss today is the Astronomical Telescope, which aims to look at very distant objects instead of ones that are very close. And the primary function of this telescope is therefore different than the microscope. You don't want to bring something tiny and enlarge it in your view. It's often actually used not so much as a magnifier, but as a light bucket. You want to collect as much light as possible from a faint, distant source. And again, what does distant means? It means we're basically looking at plane waves. And collect as much light as possible. So, in its simplest form, the telescope comes in two varieties. Refracting, which uses a big lens to collect the light, and an eyepiece. And reflecting, which uses a big mirror to collect the light, and also an eyepiece. Now there's more complex variations that use combinations of mirrors and lenses, but we're going to focus on the simple reflector and the simple refractor in order to get the fundamentals down. So let's have a look at this refracting telescope. The basic setup is we have two lenses, as before. Also as before, the first one is called the objective, and the second one is the eyepiece, with focal lengths FO and FE. Now in this case, we're going to separate the lenses by the sum of their focal length, so that the tube length, which is not a standard for telescopes, is FO plus FE. Now remember that we have objects at infinity. What does that mean? It means that each point on that source is emitting spherical waves that are so far away that they're infinitesimally small. The curvature, rather, is so infinitesimally small that it can be completely neglected. So a given point on the star or the moon or whatever we're looking at emits a set of parallel rays coming in. So in a ray picture, that looks like this. We have our incoming rays, and they're going to bend to meet the focus. And since on the other side, and the flip side, we have beams converging from the focus, they're going to come out collimated. So that initially, if we had a beam, we just considered part of a beam of width, I don't know, we'll call it W1. It's going to come out as W2, which is typically less than W1 based on this arrangement here. So here we see the light collecting power of a telescope. We're looking at the beautiful night sky one night, gazing at some star, Polaris, say, up in the north. I think it's about 400 light years away, and it has some radiant flux, which is spread out over the whole sphere, over that whole 400 light years. Let's try to sketch that. Yeah, that's as good as it's getting. Okay. So we have this sphere of light with radius 400 light years. How much of that light do we get? Well, that entire surface has a given amount of light, and what share do we get? Basically, we get the portion of that area of that entire sphere that our eye takes up, our iris, actually. So d is the diameter of our iris and our eye, and big D is the distance of the star. Our share is, there's our iris there, not to scale. Basically the ratio of the two areas, which is the d over the distance to the star, all squared. A very, very small amount of light, but there's plenty of photons. If you look up in the night sky, you can see Polaris, because the star is so bright. But now let's put a big lens in front to make our telescope. The amount of light hitting our eyes is now given by the diameter of the objective, not our iris. Because we have light coming in here, which is getting compressed into a smaller area. So how much is it compressed by? Well, that's given by that width 1 divided by width 2, all squared, right? All that area of that flux coming into that circle, that lens, is now in a smaller area. So we get a brightness increase, a light enhancement given by the W1 over W2. So how do we write this in terms of the objectives, we can do it simply by geometry. Let's have a look. We see that these two triangles here are similar. Let's call H1 the half waist of the incoming beam, or width, and the other one H2. We see that H2 over the focal length of the eyepiece is equal to H1 over the focal length of the objective. And of course we can multiply both sides of that equation by 2 to get the widths. So we get the ratio of the widths is equal to the focal length of the objective divided by the focal length of the eyepiece. And our light collecting power then is that squared. The key is that we're compressing a larger area of light and fitting it into a given area, a CCD or whatever we're looking at. Okay, so that is the light collecting power of the telescope. Now, common use of this, actually, as I've used it in the past, I'm not an astronomer, I study quantum optics, so how I use a telescope and how we've used telescopes in the lab is to actually change the waist, as it's called, the width of a laser beam. In this context, it's called a beam expander, but it's really the same instrument. You can also tweak it slightly if the beam is diverging or diverging or converging slightly. You can just tweak the location of the eyepiece or the second lens so that it is collimated. And the formula for the beam expander is precisely this. You have a 1 millimeter waist laser pointer and you need a 3 millimeter. Well, you'll use a, for example, 150 millimeter focal length lens and a 50 millimeter focal length lens. Put the 50 first, then the 150, and what you'll get is the output, which is 3 times bigger than the input. Okay, so a little variation on this idea is what's called a terrestrial telescope or a Galilean telescope, where you use a diverging lens in place of the eyepiece. And that makes a more compact apparatus. It also has the effect of not inverting the image, which is nice when you're looking at ships far away. Otherwise, the ocean will look like it's in the sky, and it would be a bit difficult to manipulate. It doesn't really matter so much if you're looking at the stars, but if you're a pirate sailing the seven seas and looking through your telescope, you don't want those images to be inverted. So in that case, you use a variation, a Galilean telescope. Still, you have the exact same formulas, where you place the lenses the sum of the focal lengths away, but now the eyepiece has a negative focal length. And since you have a negative eyepiece, that leads to a smaller distance between the two lenses. Now, we've been concentrating on light collecting power, but anybody who's looked at the moon through a telescope can tell you that they also make things look bigger, i.e. they take up more angle, if we remember our discussion from the simple magnifier. So what is the angular magnification of the telescopes? So let's have a look at that case. Let's say we have the moon over here, and our telescope, which is obviously not to scale. This moon is at infinity away, but this is just representing the angle that it's taking up. Let's look at that angle. Okay, so here's the tricky part. We're at infinity, so that point on the moon is really just a bunch of rays that are coming in parallel, and they're going to form an image right near the focus of the moon. So the original angle, we'll call that alpha. From geometry here, that alpha is about equal to the image size, we'll just call it h for now, divided by the focal length of the objective. Now that's going to get focused on the other side so that the beams emerge parallel. That's what the telescope is, right? Okay, so parallel beams coming in will remain parallel coming out, as is the case from this. This is, by the way, called confocal configuration, because our separation is the same as between the two foci. And what's our new angle? What's our new rise over run? Well, let's just zero in on this angle here. It's the same as this one. We'll call that alpha prime. Now, what are these two angles? Alpha is equal to h over f naught. Alpha prime is that same height now. We don't even care what the height is. It's the same one over the focal length of now the eyepiece. All right, so this gives us an angular magnification. Means it makes something look bigger. The apparent angle that an object subtends in your field of view compared to without the telescope is alpha prime over alpha, and that's f of your objective, divided by f of your eyepiece. Okay, finally, let's move to the reflecting telescope. We're going to use mirrors now as our objective instead of a lens. So the most basic is called the Newtonian reflector. I guess Newton made one. We have a big reflective mirror as the objective. And the whole advantage of this, and really reflecting mirrors in general, is that reflective mirrors can be made so much bigger. We don't need a big piece of glass because the light doesn't have to transmit through the whole thing. We need a very thin layer of reflective coating, which can be sitting on top of a really sturdy, lightweight frame. And it's also much easier to individually make little panels like this and then piece them together to make giant mirrors, and therefore giant objectives this way. Now the optics and the formulation and the magnification is basically the same for both. So here's a sketch of how the Newtonian telescope works. We have a giant reflecting mirror here, and we're going to use the interesting fact about parabolas, or rather paraboloids. That's the fancy word for what you get when you rotate a parabola. Anyway, when you have a paraboloid and you have incoming parallel rays like this is actually the definition of a parabola. There's a point called the focus, which is the locus of all these reflected rays here, and so on and so forth. So we have light coming in, and all the reflected beams are going to come to a point. That's our focus. Now, of course, we need to get at those somehow, and there's a few ways of doing that. One of the ways is to put a mirror floating in the middle of the tube here, which is legit. People do that. Another way, a more common way, is to have a small reflecting mirror that just takes up a portion of the area, a very small portion, here, and we cut a little hole out of the tube, and what do we get? So now we've just redirected that focus out, and then of course we're going to put our eyepiece right here. And that will now converge these rays coming out. Now, I mentioned that the primary mirror should actually be a paraboloid, and it's actually not too bad to make these. The way it's usually done is you make the large reflecting mirror a sphere, and you can do this by hand. In fact, when I was an undergrad, I made a mirror by hand, and I made my own telescope. It's very easy to grind a sphere, it turns out. You can kind of just rotate around a table. Randomness and the inability of the human hand to do something exactly the same every time tends to average out in such a way that you grind out naturally a spheroid out of the mirror. And then what you do is you put a small correction to the center of the mirror to make it a paraboloid. There are other ways of getting around this. Sometimes you just use a spherical mirror. So here we have a paraboloidal mirror. We can also use a spherical mirror, which is much easier to make for a very big segment. We're actually going to cut a hole out of the center of that mirror, and we'll put a specially shaped mirror here, which will correct for any deviations from a sphere and turn it to the rays that you'd get exactly from a paraboloid. And then it's going to come out just so after hitting this mirror, this so-called Schmidt corrector. So this type of telescope, let me just sketch it, the rays here. This design here with this corrector is called a Schmidt Cassegrain. I don't know if there's a D there or not. Is there? I think there's a D. German's hard. Schmidt Cassegrain design. And there's a number of different designs which accomplish this. For example, here's what the Hubble telescope looks like. We have this large primary with a hole in the middle, and we have this corrector here. And telescope design is a whole nother can of worms. But the whole idea is that you want these fancy optics to correct for so-called aberrations in the imaging that you get from not being paraxial or not having perfect geometric shapes. And those imperfections in lenses and mirrors are the whole subject of aberration theory, which will be the whole subject of our next and final lecture.